Okay, so we'll go through this section. I wasn't gonna go through this section, but I think maybe it'll be a fast section. Couple of theorems. Extensions to the invertible matrix. Mm-hmm. Okay, I think I did some of these. All right, so let's just get into it. It actually seems like a longer section than I realized. All right. Theorem 9 in section 4.4 implies that a vector space V with a basis B containing n vectors is isomorphic to Rn. This section shows that this number n is an intrinsic property called the dimension of the space V and does not depend on the particular choice of basis. The discussion of dimension will give additional insight into properties of bases. The first theorem generalizes a well-known result about the vector space Rn. If V has a basis of n elements, then any set in V containing more than n vectors must be dependent. Okay, so there's just a non-trivial solution. Okay. Theorem 10 implies that if a vector space has a basis, then each linearly independent set has no more than n vectors. And now we show that it's exactly n vectors. Let B1 be a basis of n vectors and B2 be any other basis of V, then B1 is a basis of, and B2 is, since B1 is a basis and B2 is linearly independent, B2 is no more than n vectors by theorem 10. Also, since B, oh yeah, okay, so that's a quick proof. Cool. If a non-zero vector space V is spanned by a finite set S, then a subset of S is a basis for V. Okay, P is infinite dimensional. Okay, then we have this plane in R3. The dimension is 2 because they're linearly independent. And they, okay, cool. All right, here we go. Here's an example. Find the dimension of this subspace. All right, so you write it all out. We can discard 3 because it's a multiple of 2. Okay, that's okay. Cool. Subspace of a finite dimensional space. The next theorem is a natural counterpart to the spanning set theorem. Let H be a subspace of a finite dimensional vector space V. Let H be a subspace. Okay, subspace of V, and any linearly independent set in H can be expanded if necessary to a basis for H. Also, H is finite dimensional. Okay, that's pretty obvious. You can always just like figure out how what vectors to add to make it so that you span some space. But it has to be a vector space. It can't just be any set. All right, the basis theorem. Let V be a p-dimensional vector space. Any linearly independent set of exactly p elements is automatically a basis. Any set of exactly p elements that spans V is automatically a basis. Okay. Dimensions of null space, column space, and row space. Since the dimensions of the null space and the column space of an n by n matrix are referred to frequently, they have specific names. The rank of an m by n matrix is the dimension of the column space, and the nullity is the dimension of the null space. The pivot columns of a matrix A form a basis for col A. The pivot columns of a matrix A form a basis for col A. So the rank of A is just the number of pivot columns. Since a basis for row A can be found by taking the pivot rows. Wait. The pivot columns of matrix A form a basis for col A. Yeah, that's right. So the rank is just the number of pivot columns. Since a basis for row A can be found by taking the pivot rows from the row reduced echelon form of A, the dimension of row A is also equal to the rank of A. Okay. The nullity of A might seem to require some work, since finding a basis for the null space usually takes more time than finding a basis for the call space. Okay, let A be an n by n matrix and suppose that the equation AX equal to 0 has k free variables. Okay, so then you just take the number free. The rank of an n by n matrix is the number of pivot columns, and the nullity is the number of free variables. Since the dimension of the row space is the number of pivot rows, it is also equal to the rank. All right, so here we go. The rank theorem. The rank plus the nullity is equal to the number of columns. Okay. Seven. Oh, yeah. This is cool. Okay, so could a 6 by 9 matrix have nullity too? So that would mean that it's um that would mean that it's rank is 7, but it can't have rank 7 because there's only 6 rows. But the columns of okay, so here. But the columns of B are vectors in R6. And so the dimension of col B cannot exceed 6. It's rank okay. We'll learn that row A and null A have only the 0 vector in common and are actually perpendicular to each other. Whoa, really? That's wild. The rank theorem is a powerful tool for processing information about systems of linear equations. The next example simulates the way a real-life problem using linear equations might be stated without explicit mention of linear algebra terms such as matrix, subspace, and dimension. A scientist has found 2 solutions to a homogeneous system of 40 equations in 42 variables. The 2 solutions are not multiples, and all other solutions can be constructed by adding together appropriate multiples of these 2 solutions. Can the scientist be certain that the associated non-homogeneous system can the scientist be certain that an associated non-homogeneous system with the same coefficients has a solution? Okay, the invertible matrix, the various vector space concepts associated with the matrix. All right, so the columns of A form a basis. All right, so it's n by n, and all of the following are equivalent to the statement that A is invertible. The columns of A form a basis of Rn. The column space of A is equal to Rn. The rank of A is equal to n. The nullity is equal to 0, and the null space is just the 0 vector space. Okay, practice problems. This is false. If S spans V and T is a subset of V that contains more vectors than S, then S is linearly dependent. No, not necessarily because, well, yes. Yes, that is true. All right, let H and K be subspaces of a vector space V. In section 4.1, exercise 40, it is established that the intersection is also a subspace. Prove that the dimension of the intersection is less than or equal to H. Okay. Well, it can't be more than it, right? Because the biggest an intersection can be is itself, so it has to be less than or equal to H, the dim of H. Okay. Ugh. Ugh. All right, so let's hop on to this. Okay, so problem one. So this is going to be 4.5 vec space dimension. So we're going to have s minus 2t, s plus t, 3t, and this is going to be, so A, basis, B, dimension. Okay, so this is going to be s, t, and r. Okay, so we're going to get, so s times 1, 1, 0 plus t times minus 2, 1, 3. All right, so this is, so then a basis is literally going to be 1, 1, 0 minus 2, 1, 3. So that's the basis. This is A. Then the dimension, 2. They're linearly independent because you can't multiply it. They're not multiples of each other. Okay, let's just do 3. I'm not going to do all of them. All right, so 3. I'm going to get, so it's not clear though because that could be dependent, right? So I don't know if we're guaranteed that the matrix 0, 0, 2, 1, minus 1, 0, 0, 1, minus 3, 1, 2, 0. So we need to now compute the rank of this because we don't know. Because I don't think that, like, let's, like, if we were to come up with, um, is this guaranteed to be linearly independent is what I'm wondering. I think it might be actually. Okay. I Okay, so it's not. I mean, I guess you could do like A plus B, A plus B. Then you would get 1, 1, A plus B times 1, 1. So in this case, okay, so you really do actually have to compute the rank. So you can't just do that. All right, so in that case, I'll just transcribe it. I think it is though. Okay, so the dimension. So first off, this is a basis. Dim equals 3. Okay, great. Actually, let's read some more of the problems so that we get an idea of what's in here. We can do 11 and 13. We'll do 17 through 26. Huh. Okay. Um. All right, we'll do 27. I'm not gonna do 28. Find a coordinate. All right, we'll do 29 because it'll be fast. 30. Let B be the basis of P2 consisting of the first three Laguerre polynomials. Nah, we'll skip that one. Let S be a subset of an n-dimensional vector space, and suppose S contains fewer. Explain why it can't span it. All right, we'll do that. That's okay. Let H be an n-dimensional subspace of an n-dimensional vector space. Show that they're equal. Maybe that's interesting. All right, we'll do 33. 33 is easy. All right, we'll do 35. 37, we'll skip all that. Mm. 41 and 42 seem cool. More true or false? Wow. All right, we always do true or false. 43 to 48. '50 seems interesting. The dimension of the row space plus the nullity of the transpose is equal. Let H be a non-zero subspace of V and let T of H be the set of images of vectors in H, then T of H is a subspace of W by exercise 7 and 4.2. Prove that the dimension of T of H is less than or equal to the dimension of H. Yeah, because either... Yeah, because you could just have the zero map, but you can never... A linear transformation can't give you more than you already have. And then, but why? All right, 51 is good. I want to see what the formal proof of that is. But it seems obvious. Let H be a non-zero subspace of V. And suppose T is one-to-one linear mapping of V into W. Prove that the dimension of T of H is equal to the dim of H. All right. Let's get started. Okay. Problem 11. Okay, so since it's already in echelon form, this is easy. So we have 1, 2, 3 pivot columns. So that means that the null space is the number of free variables, right? So first off, the column space, call A, i.e. the rank of A is equal to 3. And the number of columns is 5. And so by the rank theorem, null of A, or the nullity, is equal to 2. The row is also going to be 3. Okay, that one's easy. 13. Let's just double check. So we're in 4.5 now. So we're doing 11. 2. Wait, what? Oh, 2, 3, 3. Yeah, that's right. Because it asked for null first. Okay, here we have 2 pivots, so our and 3 free, so we're gonna get 3, 2, 2. 3, 2, 2. Nice. Okay, now we can do just 17. The number of pivot columns of a matrix equals the dimension of its column space. That's true. The number of variables in the equation ax equal to 0 equals the nullity. That's false. It's the free variables. The free variables. Okay. 19. A plane in R3 is a two-dimensional subspace of R3. That's not true because it needs to go through the origin. If they said it goes through the origin, I would say true, but it's false. If the dimension of a vector space P4 is 4, that's false. It's not. It's 5. Okay, 21. The dimension of the vector space of signals is not 10. I think it's infinite. Yeah, it's infinite. I don't know where the heck that came from. The dimensions of the row space and the column space are the same, even if it's not square. That's true. If B is any echelon form of A, then the pivot columns of B form a basis for the column space. See, this one keeps coming up. It's false. That's false. Because when you row reduce something like that, it changes the column space. So if you take the indices of the pivot columns, then those form a basis of A. But just the pivot columns of B don't. Then, okay, 24. The nullity of A is the number of columns of A that are not pivot columns. Yeah, I think that's true. If it's not a pivot column, then it's free. If a set V1 of VP spans a finite dimensional vector space V, and if T is some set of more than P vectors in V, then T is linearly dependent. That's true. A vector space 26. A vector space is infinite dimensional if it is spanned by an infinite set. That's false. That doesn't make any sense. Okay, so let's just double check on these. I think that this book doesn't. Yeah, it just says see the study guide, but I don't know what the hell that means. I don't know what that means. All right. All right. So we got true. We have false, 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 true, false, true, 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 false. Okay, cool. We got them all. Okay. 27. Show that the first four Hermite polynomials form a basis of P3. Okay, so we're going to get 1, 0, 0, 0. Then we're going to get 0, 2, 0, 0. Then we're going to get minus 2, 0, 4, 0. And then minus, or 0, minus 12, 0, 8. You know what? I'm actually curious. If we go to or actually, wait. Let's just do both. Out of curiosity, I always like to do both. Hermite. Oh, wait, you can probably just give it a list. But then you need to so I wonder if there's no Hermite. What the hell? Not Hermetian. Hermite polynomial. What? Okay. It seems like this decomposition thing is kind of gives what you want. This like does something different. That's the thing. Yeah, whatever. I don't even care. All right, so we're just gonna do this. I mean, I really would like to have. I mean, how do you generate the Hermite polynomials? That's what I want to know. Like, what are they? The Wikipedia didn't really say anything. Whoa, this is weird. That's weird. Thanks, man. Okay, so do I want to generate these? Because I feel like it'd be so much more badass. But let's just do it the boring way. So this is gonna be 1, 0, minus 2, 0. 0, 2, 0, minus 12. 0, 0, 4, 0. 0, 0, 0, 8. Then we just do rank A. Oh, wait, is it? It's 4. Okay, so it's a basis. There you go. And we could see that actually because it's already in echelon form. I don't know why I didn't see that. All right. So yeah, so there we go. So we showed that it's a basis of P3. All right, we're find the coordinate. Okay, so this is just going to be a matter of, so let's just write that. So P for 29 is equal to 7 minus 12 minus 8 and 12. So now we're going to say find P relative to the basis B of Hermite polynomials. So in that case, we have P is equal to 7 minus 12 minus 8, 12. And then we're just going to do A backslash P. Okay, there you go. So now is equal to 3, 3 minus 2, 3 halves. Very cool. Okay. What's next? 31. Isn't this just the basis theorem? I think it's just the basis theorem. By the basis theorem, any and by the spanning set theorem or whatever. All right, fine. We can skip all these boring ones. This is again just the basis theorem. All right, let's just do the true false then. These questions are more difficult than those. Okay, cool. Okay, so 43. If there exists a set that's V1 to VP that spans V, then the dimension of V has to be less than or equal to P. That's true. If there exists a linearly dependent set, If there exists a linearly dependent set V1 to Vp in V, then the dimension of V is less than or equal to P. I'm pretty sure it's false because you could just have P copies of the same vector. But then okay, 45 is if there exists a linearly independent set V1 to Vp in V, then the dimension of V has to be greater than or equal to P. That's true. That's true because if they're independent, then you got to get that space from somewhere. Okay, 46. If the dimension of V is equal to P, then there exists a spanning set of P plus 1 vectors in V. I mean, that's true. Yeah. If every set of P elements in V fails to span V, then the dimension is strictly greater than P. That's true. That's true. If P is greater than or equal to 2 and the dimension is equal to P, then every set of... That's obviously false. I don't know why they said these are more difficult. They seem like the same difficulty to me. Let's see if the book has these. Consult the study guide. So I got true, false, true, 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 false. Okay, true, false, true, 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 false. Nice, yeah, those were easy. I don't know what the heck they're talking about, man. All right, what was 50? These ones are obvious. Okay, 50 is the nullity of the transpose. I don't... Let me think. So let's say we have like... Okay, these are all obvious. All right, that's it. That is the dimension of a vector space. All right, we'll see. I might do 4.6 today. Hopefully, I can do 4.6 because I'm pretty behind because I'm supposed to be doing 5.1 and 5.2 today. but I kind of took the weekend off. All right, that's it. Peace.